Hello! In this video, we're going to go over the solutions to Codeforce's round 1006, which is a Div 3 contest. Div 3 contests have problems from easy to hard, so you should go take a look at the contest that'll be linked in the description. And then when you're stuck on the problems or you want to hear another solution, feel free to come into this video. I'm going to lay out the timestamps of when we go through every single problem here. Additionally, for this problem, I have looked at the problems and I have solved some of them in terms of solutions, but I have not coded anything up. I plan to code stuff up live with you because I feel like this contest has problems that are shorter in code length, so I should be able to code them live with you and walk you through the debugging process that I typically go through, which hopefully will be helpful. Again, if you don't want to go through the live coding process, you can skip to the end of the code, but again, the timestamps are going to be there. It's also going to be in the bar for every problem, like when we're going over the solution and when we're going over the live coding. That being said, I'm going to go through the problems from beginning to end, so it doesn't really matter how much time or effort you've put into these. We're going to discuss the entirety of the problem. Alright, so let's get started with problem A. This is a difficulty of 800. Okay, so, I feel like I'm going to butcher this name, but I'm going to give it my best shot. Let me know in the comments if I'm pronouncing it right or wrong or how to pronounce this. Is it Natsume Akito? Has just woken up in a new world and has immediately received his first quest. The system provided him with an array of n zeros, an integer k, and an integer p. Alright, so let's start by just drawing that out. Obviously, it's good to look at these samples to try to get an understanding of the problem, but it's also good to try to understand the problem without samples because it means that you're more likely to have a proper understanding of what the problem is asking. Okay, so let's just take some random values of n, k, and p. Here what I'm going to do is I'm just going to pick the first input in the sample because it seems to be kind of reasonable. So here we have n equals 21, k equals 100, p equals 10. And the first line said the system provided him an array a of n zeros. So an array a is going to be of length n. Cool. Next paragraph. In one operation, Akito chooses two integers I and x such that I is between 1 and n, and x is between negative p and p, and then performs the assignment that a of I equals x. Okay, so what is this really doing? I is between 1 and n, so that just means that I can be any index of the array. Like it can be like this index or this index, it can be any index of the array. And the next thing it says is, oops, I should make sure I erase that. And the next thing it says is that it assigns a of I equals to x. So I is an integer, and the value we change it to is between negative p and p. That's all that the second sentence is saying. Akito is not fully accustomed to controlling his new body. Oh, sorry, let's do an example of that. So we could potentially have like x equals negative 4 or x equals like 5, anything between negative 10 and 10. And this is like our value of I. We would just change this to like x. So negative 4, I'm going to change this to like 5 or something. That's the operations we can do. We can change any value in the array to any integer between negative p and p. Okay, third paragraph. Akito is still not fully accustomed to controlling his new body. So, help him calculate the minimum number of operations required to make the sum of all elements equal to k, or tell him that it's impossible. Okay, so we have n, k, and p. We want to make the sum equal to k. Alright, so in the first sample, we want to make the sum equal to 100. How many operations is that going to take? Well, we start off with an array of a bunch of zeros, right? Specifically 21 zeros. And we want the sum to be 100, with as few operations as possible. Currently, the sum is 0, and we want the sum to equal to 100. So, what can we do about this? Well, we can change this to a 10. Specifically, if we change 10 of these values to a 10, then the sum will become 100. And that's the minimum number of operations it'll take us because we can't change a value by more than 10. So that's why the first output would be 10. Okay, now a couple things to note. First of all, it never makes sense to do an operation on any value in the array more than once. We'll just change each value once to its final value, right? Why change it more than once when we can directly change it to this final value? That's the first observation. Second observation is if k is positive, then all the values that we change in our array will be positive. If k is negative, they'll all be negative. Because why put a positive value that'll just make it harder to make your sum, right? If our sum equals negative 15, we could do negative 10, and positive 5. Or we can just do negative 10 and negative 5. A positive value will only increase the maximum number of operations that it's going to take. Okay, so we want to do the fewest number of operations possible. Now, when solving a problem like this, or any problem which says if the output is impossible, print negative 1, a good starting step is to say, hey, when is it going to be impossible? And if k is positive, then it's going to be impossible if we max out the maximum possible values for every element in the array and it still doesn't equal to 10. So what is the maximum possible values? Well, if we set everything to the max, which is p, then our sum, let's put this like, our max sum is going to be n times p, because we have n values and we're going to set them all to p. So if k is positive and n times p is greater than k, then it's impossible. All right, if k is negative, then what do we want to do? We want to get the most negative sum. I'll call this the min sum, but really it's the most negative sum. The smallest possible sum we can get is going to be n times negative p, because we can put negative p in all of the n spots. If this is bigger than k, it's a little weird to think about. Think of it as like if k is like negative 100 or something, right? If this is too big, so then this side might be like negative 60. So if negative 60 is bigger than negative 100, which it is, then that means we can't put enough negative values to make the sum k. So it's impossible. Okay, so we got that starting point, and what we sort of realize is we just kind of want to max out the values to see if it's possible or not. Now, what if we know it's possible? What should we do? Well, let's say k is positive. Might be simple to think about just that, right? If k is positive, let's just say the sum we want to make equals 15, and p equals like 4. We could put a bunch of 1s, like 15 times. But that's going to be really inefficient, because we could instead not change this value and make this a 2, right? And now we only have to do 14 operations. And we can keep condensing it more and more and more. The most we can condense it to is if we put, is when we put 4. So we want to like sort of greedily, and greedy just is a method which means keep taking the best possible value. So we're going to keep putting 4s until our sum would exceed 15. So we put 1 4, our sum is like 4. We put the second 4, now our sum's 8. We put the third 4, now our sum should be 12. If we put a fourth 4, now our sum is 16. Oh no, that's too big, because we wanted a 15. So we're going to keep putting 4s until our sum gets too big, and then for the last value, we're just going to put the difference. So our old sum was 12, so this last value is going to be 15 minus 12 equals 3. So instead of 4, we're going to make this a 3. And that way, the total sum is going to equal the value. Now, if k is negative, we're going to do the exact same thing, but just replace these all with negative values. So let me show you what I mean by that. Let's say the sum we want to make is negative 15, and p is still 4. Okay. So we want to make negative 15 in as few values as possible. So you want to put the most negative values possible to sort of make this as fast as possible. So you can put negative 4, negative 4. Oh, let's keep track of the sum. So here our sum is negative 4. We put another negative 4, now our sum is negative 8. We put another negative 4, now our sum is negative 12. And then we're saying, hold on a second. If we try to put another -4, our sum is going to become -16, and that's too large. So we can't put another -4. So we're going to do the exact same thing. We're going to say, okay, we're going to just put the difference between 15 and 12. The difference between 15 and 12 is 3, so we're just going to put a -3. And now our sum is -15. So that is the algorithm for this. Let us get into the implementation. So I have my default code set up here. For the sake of this problem, I'm going to use include bits using namespace. So this just includes everything that potentially exists. I'm going to use using namespace std, and I'm going to define int long, just so that I don't have to think about if I want to use int or longs anywhere. Okay. I am also going to use this line here. What this does is it just is going to set this file here. So I can put the sample input here, and it's just going to read from this file as if this test.init file is cin. And this just makes our IO input output faster. So when I submit, I'm just going to comment out this line, and it's going to work as expected. Okay. So let's first read the input. Okay, so we have our number of test cases t, and then we're gonna repeat this t times. So we read in n, k, and p. Okay. Now, personally, what I like to do is I like to write a solve function, and this is just so that I can like, if the solve is in a function, I can then return early as soon as we have the answer. I don't have to worry about weird stuff that potentially happens in terms of, like, if the answer is -1 and I run return -1 in the middle, but then the rest of the function keeps running, I don't have to worry about any of that, because if it's a function and I return, it's just done. So we're going to print out whatever solve is. Oops. And because I'm reading n, k, and p in as global variables, I don't even have to pass anything into it. I can just say, hey, solve, and it's going to be able to access n, k, and p here. All right, so let's write our solve function. So the first thing I want to do is see if it's impossible or not. And if you recall, the way that we saw that if it's impossible or not was first we looked as if it's positive or negative. So let's do that. Let's see if k is positive or negative. Could k be 0? Okay, k could potentially be 0. I'm just going to handle that at the beginning because I don't want to have to think about it later. So if k equals 0, I'm just going to return 0. This is what I mean is, like, I can just return stuff. I don't have to think about it because I can just write more code here, and I just know that this case is already handled because it's just returning. If you were doing it in the for loop, you can do continue or something like that after, but you have to, like, print it and then continue, and you might have multiple prints in places, and it's a lot of effort. It's just a lot easier to do it this way for me. All right, so k is no longer 0. So let's handle the case where if k is, let's see, check if it is possible. That's what we're doing right now. Okay. And the reason I'm putting comments is because I'm going to link all these codes in the description so you can take a look at them after as well. Or you can take a look at them right now as I'm writing it. All right. And we have, I should set constant in maxin. Well, we don't really need to worry about this right now. Okay. So if k is less than 0, is it impossible? Well, recall the check that we did. If k is negative, we take the minimum possible sum. So if we take if negative n times p, we called it n times negative p, so I'll just do it like that. Okay, if this is greater than k, then it is going to be impossible. And sorry, this here should be if it's positive, it should actually be less than k, not greater than k. Okay, so then we are going to return -1. Slight thing about syntax here, if you only have one line inside an if statement or a for loop or anything, you don't actually need the curly brackets. So I put curly brackets here just to make it a little readable, but I think for here it's just simpler more readable if I don't. So I'm going to write code to be as readable as possible here. Okay, if k is greater than 0, and then we said if n times p is less than k, return -1. All right, so now we checked if it is impossible or not. And now let us calculate the minimum number of times. All right, so let's handle the k is positive case first. Actually, just to keep it simpler, we're going to put k is positive first here as well, just to keep it pretty standard. Okay, so if k is positive, what did we want to do? Well, we wanted to keep putting, like if k is 15, right? This should be k. We wanted to keep putting the value p until we ran out of space. Okay. So how do we count the number of times that this will actually take? Well, one thing that we can see is we could just do a loop, right? We could just say, we could just loop for p, 1 through n, right? However, we can actually do slightly better. Like, instead of placing this 1 by 1, we can see something like if we do 15 divided by 4, that's going to equal to 3 remainder 3. Notice that this 3 is the number of times we put the 4s here, and this remainder 3 is the value that goes here. And that's not a coincidence. So when we do like k divided by p, that is going to give us the number of, like this whole number is going to be the number of times we can place p, and the remainder is going to be the last value that we put. So actually what we can just do is we can do k divided by p and round up. And I mean, if you find this confusing, you can just loop from 1 to n, keep putting the value p, but this method here also works. So we're going to return k divided by p. How do we round up? So as you might know, if you just do k divided by p and they're both integers or longs here, what it's going to do is it's going to round this to the nearest int. And we don't, it's going to round it down to the floor, and we want to round it up to the ceiling. So I'm going to give you a trick to round up to the ceiling. If you want to do a over b and you want to take the ceiling, what you can actually do is you can say a plus b minus 1 over b. Now, what is this going to do? There's two cases, and the floor of this obviously, which your code does. And there's two cases to consider. One is where a is divisible by b. In this case, what is this formula going to give us? Well, in this case, this b minus 1 over b is not going to really do anything. It's going to be 0 because we're rounded down. So this will just give us a over b. In the case when a is not divisible by b, in this case, we want to do a over b and then plus 1 to it, right? If we take the floor of a over b and then plus 1 for this like extra remainder value. So in this case, what it's going to do is it's going to say, okay, this a over b is going to be it's going to be too small. But there's going to be at least 1 left over, potentially more. And that 1 left over, when you add it to b minus 1, well, now this is going to add 1 to your formula. And so this is a simple way to get the ceiling. So we can just do k plus p minus 1 over p. Okay. Now we can do the same thing if k is negative. We'll just do the same thing in a similar fashion here, but we're putting negative p instead of p. Now, I want to suggest something to you. And remember how we said earlier that it doesn't really matter if k is positive or negative? Because if k is negative, we're just going to put negative values everywhere instead of positive values, right? So what does that mean? Well, what it means in practice here, because look, when k here is negative, we just put negative values, the exact same positive ones here. And that's always true. If we make k negative, if you want to make the sum negative, right, k is just a sum. If you want to make the sum negative, we'll just multiply all the values by -1. And so what we can do here is we can just say if k is less than 0, k equals k times -1. So now k is always going to be positive. We just took the absolute value of k. Cool. So now we don't need to check this case here where k is negative. We can just get rid of it altogether. We don't need to check this case here if k is negative. We'll just always return this amount. You don't need to check if k is positive here. Cool. And because we've gotten rid of the negative and positive case, now 0 just doesn't fall randomly in the middle, right? Now if k equals 0, obviously this is not going to be true because n times p is not going to be less than 0 because they're both positive. So k is 0 is just going to return 0 here. So we don't even need this special case. All right, so now we have a lot simpler code here. So let's run it on the sample. All right, and this gives us 10, 1, 4, 6, 0, -1, 1, and 1. All right, let's gonna submit, and I'm gonna move this tab to the side because I don't want to be revealing all my files. Oh, we need to comment out this line so that it actually reads from standard input. Cool. All right, and it has been accepted. Congrats, we have solved problem A. Let's get on to problem B now. After completing the first quest, Akito left the starting cave. After a while, he stumbled upon a goblin village. Since Akito had nowhere to live, he wanted to find a place of housing. It is well known that goblins write numbers as a string of characters of dash and underscore, and the value represented by the string is the number of distinct subsequences of the string s that are equivalent to dash underscore dash, which looks like a goblin face. And then they give an example of this string here, which has 6 possible subsequences. And the way they draw it, the way they explain it is a little bit unclear, so I want to make sure that we're all understanding and on the same page. So one possible subsequence will have 1, 2, 3. You can have 1, 2, 3, that's the second one. You can have 1, 2, 3, that's the third one. You can have 1, 2, 3, that's a fourth one. You can have 1 through 3, that's your fifth. And you can have 1, 2, 3, that is your sixth. Okay, so initially the goblins wrote a random number string in response to Akito's question. But then they realized they wanted to take as much gold as possible from the traveler. To do this, they ask you to rearrange the characters in the string s so that the value of the number represented by the string is maximized. Okay, so we want to know how do we rearrange a particular string such that we have the maximum number of goblin faces. So if we look at the sample, the first one, which is dash dash underscore, this can be changed to dash underscore dash, so we have 1. For the second sample, since there is only one dash, we can never make a smiley face, so the answer is 0. The third is a little more complicated. So, in the third, we have 6 dashes and 3 underscores in total. And they're saying the answer is 27. So, when working on this problem and trying to work through it, a good step here is to stop and figure out how does this sample right here give us an output of 27. Now, here is one thing that I have observed about the problem, which will probably help us answer this question. So let's first draw. This is how we make 27. Now I'm just sort of telling you the answer here, but I'm going to walk you through the process of how to sort of come up with this on your own. And the reason this makes 27 is because, so we have 3 spots in our smiley spot, right? Spot 1, 2, and 3. Like our dash, underscore, dash. Oh, I realized I put lines underneath them, which could be confusing. I'll just draw a singular line. Okay. For the first spot in our smiley face, we have 3 possible options. For our second spot, we also have 3 options. For our third spot, we have 3 options. 3 times 3 times 3 equals 27, and that is the answer. Okay. Now, why do I think that this is the optimal scenario? So let's work through this. What happens if we take one of these? Or I guess let's start with this. What happens if we take this underscore and we move it to the beginning or the end? Well, now this underscore can't be part of any smiley faces, and that is bad. So we want the beginning and the end to be a dash for sure. Okay, what if we take all of these underscores and move them here to the middle? Well, now let's check. What are our number of options for the first, second, and third, right? So now we're going to have dash, 3 underscores, and then 5 here. So our first has 1 choice. Our second has 3 choices, and our third has 5 choices. So that means there's 15 possible smiley faces, which is less than 27. Specifically, you probably know that the way to optimize a product like this is if you put a similar amount of values at the beginning and at the end. Now, the one part I haven't really addressed here is why do we want all of these to be continuous? And the reason is that we don't get a benefit from splitting them up. So let's say we take a scenario like this, and we decide that we want to move this one here in the middle. What does that do? Well, right now, this one is part of 9 smiley faces, right? It's the first one, and then this is 3 possible seconds, 3 possible thirds. So right now, this contributes 9 to our answer. Like if we remove this, our answer would go down by 9. If we move it, say, somewhere here in the middle, so we have dash, dash. Okay, how much does this contribute to our answer now? Well, let's count. So, it has 2 possible places. It can either be the first or it can be the last. So if it is the first, then there's 3 options. If it is the last, then there's 2 options for the first, 2 options for the second, which means 4. So it contributes 7 to our answer. So our answer has gone down by 2 because previously it was contributing 9 to our answer. And so if we keep things together, we're essentially making sure that, like, as we move this over, we're just losing possible smiley faces. Because we want this to be a part of as many smiley faces as possible, right? If we shift this over by 1, essentially what we're doing is we're losing these 9 and we're replacing it with a smaller number. Because if we put this at the end, now this one here only has 2 starting smiley faces instead of 3. And that is not good. That's essentially what's affecting our answer. So for this problem, since we know we want to put some dashes, and then some underscores, and then some dashes, and we know we want the number of dashes here to be about the same, what we can do is count underscore, count dash, and then we know our pattern. Let's just say we have A of these and B of these. So then we know our pattern is going to be B over 2 dashes, then A underscores, and then B over 2 dashes. If B is odd, it doesn't matter where you put the extra dash, as long as you put it somewhere. All right, so let's get into implementing this problem. Okay, so let's put our input where we can test it. Cool. Okay, so we have our value t, n, and we have our string input. And we'll just read these in. All right, so we've read in n and input. Now we want to basically solve it. So we need to count. If you recall back to this here, what we want to do is we want to count the number of dashes and underscore. Okay, so let us loop through the string. And then we will check if the current character is a underscore. In this case, what we will do is we will say count under plus plus. What this statement here does, all it means is it means count under equals count under plus 1. All right. Else, it's a dash, so we'll do count dash plus plus. And let's just verify that the guaranteed is only underscore and dash. Yep, it is guaranteed. Okay, so now we need to figure out how we are going to divide up our string. So we have, and this is basically count under, and this is count dash. Okay, so we can, oops. All right, so we know that how many, let's call these region 1, this is the leftmost one, then the region 2 is the middle one, then region 3 is the right one. So region 1, we're gonna put count dash over 2. Region 2, we're gonna put count under, so we're putting all the underscores here. And then in region 3, we're gonna put however many dashes there are, but we're going to subtract out however many we've already put in region 1. Now the reason I don't just say count dash over 2 is because if count dash is an odd number, this will round down and the extra one will just be counted here. Okay, so now our answer is going to be region 1 times region 2 times region 3. All right, let's run this and verify it works. Ooh, did I have? Oh, I see. I'm just gonna replace these two to say count because it seems like in the other places I spelled it out. Oh, and I need to remove that. Okay. Let's check this with the sample output. And this looks correct. All right, perfect. So I'm gonna comment this out. And then I'm going to submit problem B, and I'm going to do it on the side here because I would prefer if I don't just share my folders, even though I know you guys are all wonderful people, just for my sake. All right, perfect. We have got problem B down. Let's move on to problem C now. Okay, problem C. Akito still has nowhere to live, and the price for a small room is everywhere. I'm just gonna ignore that and imagine they just said the price is large. For this reason, Akito decides to get a job at a bank as a key creator for storages. In this magical world, everything is different. For example, the key for a storage with the code NX is an array A of length n such that the OR of all the values in A equals x, and MEX of all the values in A is maximized amongst all such arrays. Now, if you're not familiar with bitwise operations, you should go learn them. I believe I don't have a video at this moment on bitwise operations on the channel, but we are in the progress of making one. So hopefully, if you're watching this quite a while after it's made, it might be up and you can just search it on our channel, but if not, tons of resources online. All right, Akito diligently performed his job for several hours, but suddenly he got a headache. Substitute for him for an hour. For the given n and x, create any key storage with the code nx. So we are given n and x, and we want to create this array A. That's essentially all we're trying to do. Now, supposed to be familiar with the bitwise OR operations. MEX is a little bit less common, so I want to take a moment to go through it. MEX of S is the minimum non-negative integer z, such that z is not contained in the set X. So, for example, if we have something like 0, 1, 3, 5, the MEX is going to equal 2, because 2 is the first non-negative integer not in this array. If we didn't have 0, now the MEX is going to be 0, because 0 is the first non-negative integer not in this array. And the array doesn't have to be in sorted order, I'm just doing it to make it clear now. So if we're trying to maximize the MEX, this means that we want to include the largest subsequence of like 0 to a certain value, and then we're going to be missing a value. The first value that we're missing that we don't have in increasing order from 0 to like infinity, that's going to be the MEX. It's worth noting that if our array has length n, the max MEX is going to be n. And this is going to be if we have 0, 1, 2, all the way to n minus 1, then our MEX is going to be n. Okay, so let us take a look at this. So we want the bitwise operation of all the values to be x. And we want to maximize this, maximize the MEX, and we have n values. Now, the bitwise OR operation is a little bit interesting. So if this was XOR, this would be a lot simpler problem. I'm not going to go into what XOR is here, so if you don't know about it, don't worry about it. If you are, exercise for the reader on how you would solve it in that case. But in this case here, what we have is to take the OR of all the values and we want it to equal x. And we're just trying to maximize the MEX. Okay, so one thing to note is that we can just add a bunch of, like, let's say our answer has a length less than n. The length of x less than n. We can just pad our answer with a bunch of zeros, n minus x zeros, and this won't affect the answer at all, because the bitwise OR will still remain the same, and the MEX will also still remain the same. So that's one interesting thing to look into. Okay, so the next thing is that we want to keep taking, we want to get the maximize the MEX and keep taking the OR of them. So we'll first add 0 to our array, right? And then we can add 1, then 2, then 3, so on and so forth. We're going to keep adding these values because that's going to maximize the MEX. But at some point, there's going to be a value that we cannot put. There's going to be a value such that if we include this value, then this first condition, where the OR of all of them equals x, is going to become impossible. And what that happens is, if you know how the bitwise OR operation works, let's say our value of x in base 2 looks something like this. Okay, if the value that we're trying to add has a 1 in this spot right here, it's never going to be possible for the OR of all the values to equal x. Let's say x had a 1 here. Okay, so now if our value we're trying to add has a 1 in any of these 0 spots, it is going to be impossible for our OR to equal x. So the MEX that we have is going to be the smallest value that has a 1 in one of the spots that x has a 0 in. In this case, our MEX is going to equal 1, 0, 0. And the reason is, let's just make this a little clearer one. The reason is, if we try to add a 1, 0, 0, the OR of all the values can never be x, because this value is going to be turned into a 1 when we OR them together, and x has a 0 here. It's impossible for that to change back. The reason we can have anything smaller than 1, 0, 0 is because everything smaller than that is just going to be ORed together, and x has a bunch of zeros here, so it's perfectly valid. Okay, so once we find the MEX, essentially what our array is going to look like is 0, 1, 2, all the way to our MEX. Oh, sorry. All the way to our MEX and minus 1. We cannot include this value. And then we can put our value x in the array, and then we just put like any sort of garbage to pad the arrays. We can just put a bunch of zeros. It doesn't really matter. And that is essentially the solution to this problem. It does seem a lot simpler when put like this. However, I think the difficulty in this problem comes from knowing how OR operations work. Like, the sort of key observation here is that if you OR any number which has a 1 where x has a 0, then it's going to be impossible. And that's how you determine your MEX. So your MEX can just have 1s everywhere else. And then at the end, we're going to OR it with x to make sure it has 1s in all the right places. So we want to make sure that we do catch these ones, right? We can get that by just ORing it with x. Okay, so this takes care of most cases, but what happens if x is devised in such a way that, like, this is impossible, right? Like, what if MEX equals n? The reason this is a special case is now if we try to make this array 0, 1, 2 all the way to MEX minus 1 and then x, now this has n plus 1 values. And that's too many. The solution is we're just going to cut off MEX plus 1 minus 1. So now we're only going to have n values. All right, so let us implement this problem now. So the input that is given is n and x. So we have t test cases, and then we're going to read in n and x. And then what we're going to do is we're going to output this array here. The first thing you want to output is, actually, it's just the n values. So in the first input, we get 69 here. For the second one, we have 7 values. Third one, we have 5 values, and so on and so forth. So the easiest way we're going to have to do this is we're going to have just a vector. This would be array list in Java, or just a normal list or an array in Python. So a vector in C++, which is going to have our answer. And then we're going to say answer.clear. So we're going to empty it so that we can restart. Then we're going to solve the problem, and our solve function is going to fill answer with our answers. And then we're going to output it in this case here. So for int I equals 0, I is less than n minus 1. Now, I said n minus 1 on purpose because for the first n minus 1 values, we're going to put a space after it. So we're going to see out answer I, and we're going to see out a space. For the last value, we're going to put a new line after it. And that's just how they want it formatted here. I forget if Codeforces is actually complains if you put extra white space on the end or not. Some judges, online judges do, some don't. Codeforces may not complain, but if it doesn't complain, you can just go all the way to n. Actually, if it doesn't complain, you can just loop through the values of the vector directly and print them with a space and a new line at the end. But anyways, we're just going to do it this way for now. Okay, so now we need our solve function. All right, so we have our value x, and we want to know what values we can potentially add, right? So, if we look here, we want to keep adding all these values up until an MIX. So let's just try to start and do that. Let's start adding values from 0. And we said that if our MIX is n, that is actually going to cause an issue. So we're only going to go up to n minus 1 as our possible MIX. Okay, so now we're gonna see, does this value, like if we add this value to our array, will it break this OR condition here? So we're just gonna check if I or X is not equal to X. This means that adding I is gonna break it. This means that adding I, because when we OR it to X, we're essentially checking, like, does I have any bits that are 1 that X doesn't? If this is not X, that means that I has some bit that's 1 that X doesn't. So if this is the case, then we just want to break. Our MEX thing is done. Else, actually we don't really need an else because the break will just exit the for loop if this condition is not met. I'm going to say ans dot push back I. Okay. Cool. Now, the next thing that we have to do is we have to see, so like, let's say that we want to check if it's possible for the MEX to be n or not, right? So actually, okay, let's ignore that for a second. Let's assume the MEX is not going to be n, just to keep life a little bit simpler. So we added all these values, 0 to MEX minus 2, basically. And then we'll do ans dot push back X. And then until there are n items in answer, we're just going to add some zeros at the end. Okay, so let's try this on some samples. And there is one case that this does not cover, and that's going to be this test case 2 here. I'll get to how we're going to do this in a second and what the issue is, but let's just test it out on this for a second. The only case we haven't actually covered is what happens if the MEX is n. Because recall, we just removed MEX minus 1 from there so we can fit X. So we'll deal with this in a second, but yeah. Oh, there should be capital X. All right. Oh, it says we need to put this around these to evaluate it. There we go. Okay. So the first output is right. The second one, the MEX is actually n, so it's an issue. This one, the MEX, is n, so it's an issue. This one, it is correct. This one, I believe it's correct. The MEX is n, but that's also like 7, so it's not really an issue. This one is also correct. This one, I believe, is also correct. I believe this is correct as well, as is this. Yep. Cool. So as long as the MEX is not n, we've dealt with this. How do we deal with the case where the MEX is n? So since this is just one specific case, we can actually just try it directly. Like, we'll just try 0 or 1 or 2 or 3 all the way to or n minus 1. And if this equals x, then the MEX is just x. So we can just test this right here. I think the simplest way to implement this is just add a check if the MEX equals n. Case int all or equals 0. So we'll just all OR them together. If all of them OR together equals x, then this means that the MEX can be x. So now what I'm just going to do is I'm just going to add all of them to an array, or add all of them to our answer array. and then I'll just return. So this is the case where the MEX is 0, as MEX is n. This is the case where the MEX is not n. All right, let's verify that. Oops. Oh, this should be a capital X. All right, so now this case here looks correct. This is this. Yep, they look correct. All right, so let us submit this. Once again, I'm just gonna bring it to the side to hit submit real quick. Okay. Nice. All right, we have officially solved problem C. Let's move on to problem D. So, problem D, for the wizards, the exam is easy, but I couldn't handle it. Okay. Akito got tired of being a simple locksmith at a bank, so he decided to enroll in the Magical Academy and become the best wizard in the world. However, to enroll, he needed to solve a single problem on the exam, which the ambitious hero could not manage. In this problem, he was given an array A of length n. He needed to minimize the number of inversions in the array after applying the spell exactly once. If you don't know what an inversion here is, an inversion is simply a pair of indices that are in swapped order. So, for example, you can read their formula here, but basically, let's say you have an array like 2, 1. This is an inversion. So if we have the array B that they're given, 3, 1, 4, 1, 5, anytime a value on the left is greater than the value on the right, that's an inversion. So this is an inversion, this is an inversion, this is an inversion. There's 3 inversions. Okay, so he needed to minimize the number of inversions after applying the spell exactly once. The spell was simple. To apply it, Akito had to choose 2 numbers, L and R, and perform a cyclic shift of the subarray from L to R, 1 position to the left. So that just means he's gonna, like, let's say that he picks this segment here. A cyclic shift 1 position to the left means everything just moves to the left, and the leftmost thing cycles over here to the front. So this would make our array 3, 4, 1, 1, 5. Akito is eager to start his studies, but he still hasn't passed the exam. Help him enroll and solve the problem. Okay, so it is guaranteed that the sum of n squared across all test cases doesn't exceed 4 times 10 to the power of 6. What does this suggest? This suggests that our algorithm is probably going to be n squared. It says for each test case, output the values of L and R. Cool. So, because our algorithm can be n squared, we should start thinking of what are different things that make sense for an n squared algorithm here. Well, one thing that would make sense for an n squared algorithm here is simply trying all possible values of L and R, right? How do we count the number of inversions if we try a potential value of L and R? Well, let's think about this, right? If we have our big array here, and we have our L and R. So we're going to do a cyclic shift of everything in this section here. Okay. All the inversions caused by items on this left here with anywhere in the array is not going to change. All the inversions caused by things here is not going to change either. In fact, the only thing that's going to change, right, is because we're moving everything over 1, and this gets moved over a bunch. The only thing that's going to change is the set of items, like is this item right here. The number of inversions it's going to change by is it is going to reduce by the number, it's basically just going to change by the number of inversions that like changes when it moves. Like the number of inversions of anything else is not going to change. It's only this one specific value. How much is going to change by? Well, it depends what's in this range here, right? So like for this example, up here, when we move 1 to the end, well, it's going to reduce by the number of things that's smaller than it in this section, which is 0 here, and it's going to increase, but the number of things is bigger than it, which is 4. So now there's now there's this 4, 1 inversion. So for this range L and R, we should just take the first value, say, hey, how many smaller things are after it, and how many bigger things are after it? So let's grab a concrete example so that this makes more sense. And I'm just going to grab something from the input here. I think this is a nice one. Actually, let's try this one here. Okay. If we shift a random range, I'm just going to say here to here. Right, so 5 is going to move here. How many inversions does this change by? Well, 5 currently has an inversion with 4 and 3. There's 2 numbers after 5 that are smaller than it. And when 5 moves over here, those 2 inversions are going to go. Now there's no inversion between 4 and 3. So the number of inversions is going to be reduced by 2. However, there's one value bigger than 5 in this range. So 5 to 8 previously was not an inversion. But when 5 moves here, it's going to be an inversion. So we do plus 1. So net, moving 5 over, reduces the number of inversions by 1. Okay, what does this mean? This means to check how good a range L to R is, we need to count the number of values between L and R that are bigger than the first value and that are smaller than the first value. The number of values that are bigger than it is what we add. The number of values that are smaller than it is what we subtract. And that's just it. That's the delta. Because for everything smaller than it, well, that's an inversion we're going to get rid of. For everything bigger than it, that's an inversion we're going to add. And so we're going to try all possible values of L and R and count this value here, the number of things smaller and bigger. Now, what's the runtime of this? Well, let's say that we try all possible values of L and R, that's n squared. And for each possible value of L and R, we loop through everything in the middle to count the number of values smaller and bigger. That's going to take another n. This will give us n cubed, and this is going to be too slow. So what can we do about this? Well, one thing we can do is, let's say that, so right now R is here, right? Let's say that R shifts over one spot here. Now we have this new value 2. Well, notice that the number of values smaller and bigger than 5 in this, actually pick a different color, in this range don't change. The only value that changes is we just need to add this value in. So we can just add 1 to smaller. So now it takes O of 1 to just expand the range by 1. So we can shift R over in O of 1. So now we have n squared values of L and R. And every time we shift R over by 1, it takes this O of 1 time. So our 1 time is going to be O of n squared. Okay, let us implement this. Okay, so we have our values in, and then we have our input vals. We don't know, or actually, we told us max n is going to be 200. Sorry, 2000. Okay, so we read in our input t, and then for every test case, we're going to read in n. Cool. So now we just need to solve the problem. So we don't know the optimal values L and R, and we don't know how much they're going to reduce our answer by. So what happens if it doesn't reduce our answer by not anything? Then the amount reduced is going to equal 0. And a potential value of L and R that can do that is if L is 0 and R is 0. If L and R are indexes, because that's just basically saying if the range we pick is just this value here, then our number of inversions are going to decrease by 0. So that's one possible answer, assuming the input's already in sorted order, right? Like what happens if your input's in sorted order? Then we would expect this to just be outputted. So again, we're going to try every possible value of L and R to see which ones reduces the number of inversions by the biggest possible value. Our starting point is like what do we initialize our variables with? Well, we're going to initialize our variables with saying nothing was reduced. And then we're going to try all possible values of L and R. Okay, so let's try all possible values of L. The num smaller is going to start out at 0, and num bigger is also going to start out at 0. And then let's try all possible values of R. So we're going to start out at R at L plus 1. Note that we could start R at L, it just would never count anything. And same thing here, we could go to like n minus 1 because we're starting R at L plus 1. None of these details actually matter that much at all. So it doesn't really matter how you implement it there. Okay, so we're trying this range L to R. So the first thing we have to do is we have to say, do we need to update num smaller or num bigger? So if vals of R is less than vals of L, then num smaller plus plus. If vals of R is greater than vals of L, then num bigger plus plus. Cool. Now we need to see how many, what amount is this changing by our inversions by. So int inversion change. Recall that we said we need to subtract everything smaller, because everything that's currently smaller, we're now gonna, we currently have an inversion, but we're gonna get rid of it if we move L over. And for everything that's bigger, we're gonna cause an inversion. So this is gonna be equal negative num smaller plus num bigger. Cool, now let's see if we need to update our answer. So if inversion change is less than the best amount reduced, we should actually call this best amount reduced. Then we're going to say best amount reduced equals inversion change. Best L equals L. Best R equals R. Then at the end, we're just going to write out L and R. Note that because we did zero-based indexing for this problem and the answer wants us to use one-based indexing, we're just going to add 1 to them. This should be best L. And this should be best R. All right, let's check this out. 2, 7, 2, 4, 1, 8, 4, 6, 1, 2, 1, 4, 1, 3, 2, 3. At the end, they're in sorted order, so 5, 5 is valid, 1, 1 is also valid. We put it 1, 1 because we initialized best L and best R at 0. Okay, so this code seems to work. Let's submit it, and I'm just gonna do so on the side to hide my folders. Nice. We have now successfully solved problem D. Let us move on to problem E. All right, let's go on to problem E. And yes, I am filming the remaining problems on a different day than I filmed the first 4. All right, so do you love your hero and his 2-hit multi-target attacks? Akito decided to study a new powerful spell. Since it possesses immeasurable strength, it clearly requires a lot of space and careful preparation. For this, Akito went out into the field. Let's represent the field as a Cartesian coordinate system. For this spell, Akito needs to place n, which is less than 500, staffs at distinct integer coordinates in the field, such that there will be exactly k pairs I and j, such that they give a formula of like p of ij equals d of ij for all pairs, and p of ij is going to be the if we have a point here and here, p of ij is the distance directly to them, and d of ij is the Manhattan distance. I know there's a name for p of ij. I just know d of ij is the Manhattan distance. I don't know what the name for p of ij is. Okay, and we want these two to be equal for exactly k pairs. The first line of input is the number of test cases, sure. For each test case, you are given the value k, and that is it. So for a test case, you're just given the value k, and you're able to place up to n 100 points. So for your output, you give the value of n that you would like, as long as less than 500, and you give the points. Okay, so let's look into this problem. First, when is it going to be the case that p of ij equals to d of ij? Now, notice that if p of ij, and if I and j have different x coordinates and y coordinates, d of ij is going to be, it's going to make like a right triangle, where d of ij is the part that takes 2 lengths, and p of ij just takes 1. So the only time that they're going to be the same is if it's a horizontal line or a vertical line. In both of these two cases, p of ij is going to equal d of ij. If it's not a horizontal or a vertical line, right, like if this is the horizontal line and it's any other point, well, now p of ij is going to be this, but d of ij is going to be this. So they're going to be different. So the only valid cases are the horizontal and a vertical line. Okay, so we want to find the number of pairs such that this, we want the number of pairs to equal k, such that they're either horizontal or vertical. So we want k pairs to be on the same horizontal and or vertical line. Okay, so we looked at the case where we have 2 points on the same horizontal and vertical line, but what if we have more than 2, right? What if we put 3 points on the same horizontal line? Now, how many pairs are there that have the same p of ij and d of ij? Well, there is 1, 2, 3 such pairs. Specifically, if we have n points, the number of pairs that are matched is going to be n choose 2, which I'm going to write in this format. If you've not seen this format, it basically just literally means this. That's the number of ways to pick 2 points from n. So, if we have like 5 points, well, we have 1, 2, 3, 4, plus 1, 2, 3, plus 1, 2, plus 1. And this equals 5 choose 2. Okay, so now we know that within, let's just say we decide to structure our output such that we have multiple columns of points. Right, so we have multiple columns of points, and each of these columns is going to have a certain number of points that that is one of these valid pairs. And a valid pair is such that p of ij equals d of ij. So each of these points have some number of valid pairs, right? So let's say that this column has points here, here, here. Okay. The issue with just adding each of these columns individually is that notice that there's some pairs between columns. And that's going to affect our answer because there have to be exactly k valid pairs. So one thing we can do to avoid this problem is we can simply take each of these columns and we can say that each of these columns, we're going to put points such that there are no horizontal matches, such that there are no horizontal pairs. And that way, now if we want to calculate the number of valid pairs, and again, valid pairs when p of ij equals d of ij, for this answer, we're just going to count, okay, this has 4 points. 4 choose 2 means that this is going to give us 4 choose 2. This is 4 times 3 over 2 equals 6. This is going to be 3 choose 2, which equals 3. This is again 3 choose 2 equals 3. And then this is also going to be 3 choose 2, which equals 3. So the total number of valid pairs is going to be 6 plus 3 plus 3 plus 3, which equals, let's see, 12 plus 3, 15. So now the number of valid pairs is a little bit cleaner to compute because we don't have any horizontal crossings, we only have vertical crossings. Now the question is, if we only put vertical crossings like this, is it possible that with just 500 points maximum, because remember, we can only put a maximum of n staffs. So at 500 points maximum, we can make any value of k up to 10 to the power of 5. Okay, so So let's look into this, right? If we want to make any amount of k to 10 to the power of 5, what do we have to do? Well, notice that if we add 1 point to this column here, the number of answers it adds is going to be 4, because this 1 point is going to make a pair with each of the 4 existing ones. So if the point is the xth point, that's going to add x minus 1 to our answer, right? So this point here would give us plus 4, whereas the point here would only give us plus 3, because it can only match with these 3. And the next point here is going to give us plus 5. The next point here is going to give us plus 6, and it keeps increasing. So if we want to make our answer like really big, notice that the number of points in a given column is like O of, if we have x points in a column, there's going to be O of x squared matching pairs. Now this is a little bit encouraging because 500 squared equals 250000, which is a lot greater than the 10 to the power of 5 that we need, right? Like the max k is this value here. So this is pretty encouraging. But we need to know, is it possible to put exactly k, right? So let's suggest the following algorithm. We're given a value of k. The first column that we're going to make is going to be the maximum column such that the number of pairs is still less than k. So this is going to be max call such that pairs is less than or equal to k. Now we might have some left over, right? Like let's say that k equals, let's say k equals 20. So the amount that we're going to put in this first call might be, let's just expand this out a little bit. Okay, what is the max we can put? Well, if we put 1, the number of valid pairs we have is 1, right? 2 is going to be 2. 3 is going to be 2 is going to be 1. 1 is 0, 2 is 1, 3 is going to be 3. And specifically, the max we can do, if we have 6, now our number of pairs is 6 choose 2, which is 6 times 5 over 2, which is 15. If we add a 7th, now we would have 7 choose 2, 7 times 6 over 2, which is 21, and that's too big. So we cannot have that. So the max number we can do in the first column is 6, so we have 15. Okay, now what we have to realize is that we have some leftover. How many leftover pairs do we need? Well, we started with k and we made 15. Which means we have 5 more pairs to make. So the second column is the max such that we don't go over the value 5. So if we have 3 points in the second column, now we've made 3 choose 2 equals 3. Okay, our leftover pairs needed equals 5, which is how many we needed originally, minus how many we made, 3, equals 2. So our last column is just going to be this will give us 1 pair. Sorry, I didn't mean the last column, the next column. Now we're going to get to our last column. So our leftover pairs needed equals, well, we needed 2, we made 1, so we subtract the 1, and we have 1 left over, and that's going to be this. So we're making 4 columns, the first with 6, then with 3, then with 2, then with 2. Right? So now, what happens if k is really, really large? Can we still do it within 500, within 500 points? What happens if k is 10 to the power 5? Well, let's compute that. And I'm just going to walk you through what I did when I was going through this problem the first time. I said, okay, let's say k equals 10 to the power 5. How many points are we going to put in the first column? Well, let's say we put X points in the first column, and let's just guess a number like, let's say like 100. And then I'm going to have it print X choose 2, which is going to be X times X minus 1 over 2. All right, so let's run this. Cool. 4950. This is way lower than our needed 185 points. So let's up this to like 300. Okay, now we're getting a little bit closer. And actually, I want to print k minus this value. This is how many leftover points we're going to have. So if n is 300, we have this many left over. Let's up n by another 100. How many leftover points that we had? Okay, leftover points is reducing. Now again, I want to make n so large that our leftover points is as close to 0 as possible. If our leftover points is less than 0, then we've gone too high. Okay, so if n is 450, that's too high. But by a little bit, it's only 1,000 over. So let's try n is 445. Okay, now our leftover points is about 1,000. So let's go up a little bit higher. Let's actually go up to 447. Ah, perfect. So if x is 447, if you put 447 points in the first column, now we have 319 left over. And to prove this is the right amount, we can put 448, and now we have a negative number left over. So in the first column, we want to put 447 points. Okay. Now, let's try column 2. So for column 2, we're going to set k equals to 319 because we have 319 left over. And we're going to try different values of x. So let's start with x equals 20. And let's print out the same thing. Okay, so if we set x equals 20 here, we have 129 points left over. That's still a little bit high. So let's set x equals to, let's try 35. Oh, that's way too high. Now the number of leftover points is negative. It's too many. We bump x down to 30. It's still a little bit too high. Let's try a little bit smaller. Okay, so if x equals 25, the number of points is 19. And I know that this is good because if we increase the value of x by 1 to 26, we're going to add 25 points to this value here. Like we're going to have 25 more pairs that match. So this will be negative 6. So it'll be subtracted by 25, right? And we can prove this by just saying if x is 26, it's too low. It's negative 6. Cool. So in our second column, we're going to put 25 points. And our leftover is 19. So we'll just do it again. You see, okay, for the third column, we have 19 to put. Let's try x equals 4. Oops, there we go. All right, now we have 13 left over, so let's up x a little bit. Now we have 4 left over. And again, if we increase x to 7, this will create 6 more pairs, because the last seventh point is going to be matched with all the remaining 6. And we can prove this by just increasing this to 7, and this should go from 4 to 6 less, which is negative 2. Perfect. Okay, so now we have 4 pairs to make. Okay, so let's try k equals 4, and x equals, well, if x equals 3, then we should have exactly 1 pair left over. Perfect. And then what we're going to do is we're going to say we have 1 pair left over, and we're going to put 2 points in the row, because we know that 2 points in the row is going to make 1 match. And, oh, is it printing? Oh, I need to save. Perfect. Now our number of points is down to 0. So how many points did we do in total? Well, our first column, we did 447. Our second column, we put 25 points. Our third column, we put 6 points. Our fourth column, we put 3. Last column, we put 2. So our total number of points is 483, which is less than the required 500. Now, I want to point something out to you, and that is that k equals 10 or 185 to the power of 5 may not be the max number of points that were ever required, right? Because let's say for a different value, this x goes down by 1, so we put 1 less point here, but then the remaining 4, 4, 6 have to match up in future columns. So when we add 1 to this first column, we're reducing the values in the future columns by a lot. And so k equals 185 may not be the max answer ever. Or sorry, may not lead to the max value of n. Now that being said, when we're in a competition, it's not the best use of time to calculate what value of k leads to the max value of n. So in a competition, we can just say, okay, for k equals 10 to the power of 5, this works and it looks like we have some left over. So for that reason, it is reasonable to assume that this algorithm is going to work. This is not a definitive proof that it works for any value of k, right? Because I said for some other values of k, less than 10 to the power of 5, the answer might be smaller, but this is good enough to convince yourself to code it up in contest. If you want to see the official, full proof and find the max value of k, I believe there's something like that in the solution, but this was enough to convince me of the solution, or of this algorithm, that this algorithm would work within 500 points when I was working on this problem. And again, like a rough estimation that this algorithm is reasonable is that 500 choose 2 is going to be a lot greater than the max value of k. And here we said 500 squared. You can really look at 500 choose 2 instead, which will be a little bit less, but it's still going to be greater than the max value of k. So that's like a good first order idea that will tell you this is worth investigating. And then once you get this is worth investigating, let's do something a little more precise. And that's what we did here to sort of convince ourselves this is a reasonable algorithm. Okay, now let us code this algorithm up. Alrighty, so for our input we have our value k. Let's see in k. Okay, so now we want the biggest value of x such that x choose 2 is less than k. So how do we compute this? Well, we can do some math here, right? We want to find the biggest x such that, and ST stands for such that, x choose 2 is less than or equal to k. Okay, so let's expand this out. X choose 2 is x times x minus 1 over 2 is less than or equal to k. And we can expand this out to x times x minus 1 is less than or equal to 2k. Okay. So this gives us x squared minus x minus 2k is less than or equal to 0. And this is an inequality that we can use the quadratic formula on to find what value of x would create this equal to 0. And so let's just do that actually. So let's just say we're trying to solve the equation, what if it's x squared minus x minus 2k equals 0? We would say, oops. Oh, this should be hk. Okay, so these are our values of x. And so we could compute these and we could get the value that's going to work. However, I'm going to make an argument that it's just a lot simpler to binary search on the value of x. If you're a math person and you want to expand this out for a given value of k and find the value of x and the biggest value of x that satisfies this inequality, fine, go for it. But for me, it's probably just easier to binary search on the value of x. Okay, so in order to binary search on the value of x, we need to know what x choose 2 is for all values of x. So I'm going to say x choose 2. And this should be max of n. And the values of x choose 2 don't actually change for each test case. So we can just compute it once and use it for all test cases. Okay, now the arrange I did here is I didn't do for 0 because actually it probably doesn't matter if you do for 0 because 0 times negative 1 is going to give you 0. So as long as x choose 2 of 0 and 1 gives you 0, it's fine. And the reason I specifically look into those is because sometimes the small values can give you weird answers. And then we go all the way up to 500. In practice, we're never going to need anything greater than 499 because we already know that 500 choose 2 is too large. But I just computed up to 500 because it doesn't really hurt. If you do less than 499 or less than 500, which is less than or equal to 499, it should work just fine. Okay, why did I compute this once here instead of doing it later? Just to make the code a little bit cleaner. If I was in a competition, I may or may not do this. If I'm being honest, I'm just doing it so that it's a little easier for you guys to follow along with the code that I'm writing. Cool. So we have int k. So now what we want to do is, so k is going to be our size remaining, right? But like, in order to keep things simple, I'm just going to create a variable called size remaining and set it to k. Again, if I was in a contest, I would probably just reduce k as I make pairs, just because it's simpler, but because we're here and I want to make sure that the code is readable to you and you can, because I'm going to link this make the video, right? So as long as you can access it after the contest and really make sense of it, it's very simple for me to just add this extra thing in. But in a contest, I'd probably just change the value of k and keep reducing it. Cool. So we have size remaining equals k. Now the next thing we need to do is start like making our columns. Okay. So while size remaining is greater than 0. So we have points that we need to match. Then the first thing I need to do is figure out this value of x for the column. So for the biggest for the current column, what is the biggest x such that x choose 2 is less than k? So let's say int x equals biggest x. Biggest x such that x choose 2 is less than or equal to size remaining. So we're going to have this function biggest x, which takes in a value size remaining, and returns the biggest x such that x choose 2 is less than size remaining. Actually, size remaining is just a global variable, so we don't even need to pass that in. Okay, so we're going to do a binary search for this. Okay, so what is the lowest possible value this can be? Well, this is going to be 2, right? Because 2 is going to be 1. And we know that size remaining is greater than 0. So the lowest possible value is 2. And the highest possible value is going to be, I'm just going to put it as 500, even though technically it's 499. Cool, so while a is not equal to b, this means while our lower bound is not equal to our upper bound, our mid is going to be a plus b over 2. And then we're going to check if x choose 2 of mid is greater than size remaining. This means that mid is too big. And we want a to b to be the range of things that are actually valid. So we know that mid is not valid. So b equals mid minus 1, because mid is not valid. else this means mid is valid, so a equals mid. And we don't do mid plus 1 because we don't know if mid plus 1 is valid or not. We say a equals mid. Okay, so here we can see that a equals mid and b equals mid minus 1. Now, what happens in the specific case where we have something like a equals 4 and b equals 5? So now mid is going to be 4, and then let's just say 4 is valid. So then we're going to say a equals mid. So now we have a equals 4 and b equals 5, and we have an infinite loop because nothing has changed. And for that reason, we're going to round up here. Mid is going to equal to a plus b plus 1 over 2. So now in this case, mid is going to equal 5. It's going to say 5 is either valid, in which case a is going to equal 5, or not valid, in which case b is going to equal 4, and the binary search won't lead into an infinite loop. In general, if you're saying b equals mid minus 1, then and this is going like minus 1, you want to add a round up, plus 1 here. If it was the case you were doing a binary search such that a equals mid plus 1, then you wouldn't include that here. But just check the edge condition, be like, hey, am I ever going to run into an infinite loop? It's a reasonable thing to check, but I've done this so many times, I just know if I put a plus 1 here, I don't need a plus 1 here. If I put a minus 1 here, I need a plus 1 here. Okay, and then we just return a. Cool. So now x equals the biggest possible x. Now, if I was writing this binary search and I wasn't confident in my binary search, like if you're someone who hasn't written a ton of binary searches, what I would do is I would just like print out biggest x for certain values of size remaining, just to verify that this function is working as expected. Because it's reasonable to test every part of your code as you're writing it, especially parts of your code that are kind of unfamiliar to you. Because if you just end up with a bug at the end of your code, you don't know where amongst the entire thing it is. Whereas if you check things as you're going, it's going to be more reasonable. So if you're someone who's not written a ton of binary search, I would recommend just testing the biggest x function right now. Okay, so we have biggest x. Cool. Now, what do we need to do? Well, we need to put x points in the current column. Okay, so the first points go into the leftmost column, and then we have this column. So we actually need to know what column we're in so that we can put the points. So let's have a value, current call, and we can start current call. So the points that we can put are x and y between 10 to the power 9, which is way bigger than we're ever going to need, so we don't have to worry about that. Oops. So here we can set current call equals 0. Okay, so we know which column we're in. Now remember, the next thing we wanted, like we know which column we're in, but the next thing we wanted is we also want to make sure that like these points are not here where they could intersect with these, right? We don't want there to be matches like this. And so we'll talk about how to handle that in a second. But let's create our answer. Let's make this actually a pair intent. Why is it? Oh, there we go. A parent int, our answer vector of points. So when we start this out, let's first empty it because last test case might have filled it up. Okay, so what we can do simply is our first point, we can put it at 0, then 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. So the ith point will just give it the y-axis of I and the x-axis of current call. And then once we're done with the call, the next column, you need to have a value of current call. It's 1 more, so we just increment that by 1. And then size remaining, we need to decrement this by the number of pairs that we've already made. That's going to be x choose 2 of x. Okay, so let us test this out. And then we need to print our answer. So the first line of the answer is going to be the total number of points. That's going to be ants.size. And then for auto x and ants, and what auto does is it sets itself to the type of the values in the vector. So for right now, it's going to be a pair int. Cout x dot first, x dot second. All right, and let's set the input. Oops. To read from our file, which has our inputs. Cool. Oh, I forgot this right there. This should be pushback. Sorry, I've been writing a lot of Python code recently, and Python uses append. Okay, cool. Let us check this out. So our first input is 0. Now, they just put a bunch of points, which don't form any pairs. So we're not actually going to use their points because it's just going to be really confusing. We can just look at our output and see if it's valid. So the first input is 0. We have to make 0 pairs. So we just printed out 0. N equals 0. And that's valid. N can be 0. Cool. Our second input is 2. We have to make 2 pairs. Oh, this does not look right. Hold on a second. Oh, wait, yeah, it is. This is 1 pair, and this is another pair. Perfect. Our next input is 5. We have to make 5 pairs. Okay, so let's see. These will create 3 pairs. These will create 1 more pair, so we have 4. So we'll create 1 more pair, so we have 5. Cool. So this seems to work as expected. So let us submit this. And as usual, I'm just gonna... Okay. Perfect. So this works. Alrighty. Let us go on to problem F. And goodbye, banker life. Okay. Monsters are approaching the city, and to protect it, Akito must create a protective field around the city. As everyone knows, protective fields come in various levels. Akito has chosen the field of level N. To construct the field, a special phrase is required, which is the nth row of the Great Magical Triangle, represented as a 2-dimensional array. We will call this array T. The triangle is as follows. On the ith row, we can have, on the ith row, there are I integers. And I'm just going to move this here so we can draw out this triangle as we are reading the problem. Okay, the first row is a single integer k. The jth element of the ith row will be denoted as Tij. So, if j equals 1, the first element of the next row, it's just going to be Ti minus 1j. So this element right here is just going to copy the one above it. And if j equals I, that means if it's the last element in the row, it's just going to be the one left and above. This is also k. All right, the third row, the first element is just the one above it. Now this one here, the second element, is going to be the XOR of this one and this one. So it's going to be 0. This last one here is just going to copy this one. Cool. Next row, the first element is again going to just copy this. The second is going to be the XOR of these two. The third is going to be the XOR of these two. Oh, let's actually line these up a little nicer. And the last is just going to copy this. All right, next row, we're going to have k, and then we're going to have the XOR of these two. and so on and so forth. So we have a column something like this. If you're not familiar with XOR, read this link. It'll teach you the details of it. For this problem, all you need to know though is, like, if you have A XOR 0, this equals A. If you have A XOR A, this equals 0. And if you have 0 XOR 0, this equals 0. These are the only three operations used in this problem. Cool. So help Alkido find the integers in the nth row of the infinite triangle before the monsters reach the city. Okay. So the first thing we can observe, and this is actually just from this triangle that we've drawn, is that it doesn't actually matter what k is. Regardless of what k is, the row is consisting of k's and zeros. So that's nice. So now we just need to know what the nth row looks like. And n is up to 10 to the power of 6. And there are n items on each row. So this means that the entire triangle up to the nth row is going to be O of n squared. And so we can't just draw up the entire triangle. That'll be way too slow for n is 10 to the power of 6. It is guaranteed that the sum of n across all test cases does not exceed 10 to the power of 6. What is this useful for? Well, when we output items on the ith row, essentially what we're doing is we're outputting I items. So what this is saying is the number of items that you need to print is not more than 10 to the power of 6. But in terms of runtime, O of n squared is still going to be too slow. Okay, so if you are familiar with something called Pascal's triangle, you might remember it looks like this, where every item is the sum of the two items above it. Right. How do we find the xth row of Pascal's triangle? Well, again, if you're familiar with Pascal's triangle, you might actually know that to find the xth row of the triangle, there is a reasonably simple formula. And you can look it up if you're interested in it. But essentially, one way I like to think about this is if you do like a plus b squared, this row will give you the coefficients of it. So it's going to be a squared plus 2ab plus b squared. Right, the coefficients of 1, 2, and 1. If you do a plus b cubed, this row will give you the coefficients. So 1a cubed plus 3a squared b plus 3ab squared plus b cubed. And so on and so forth. And essentially what this is going to be is, well, it's going to go back to the choose function that we did in the previous problem. So this third row, right, is going to give us 3 choose 3, 3 choose 2, 3 choose 1, 3 choose 0. Fourth row. This first item is 4 choose 4. The second item is 4 choose 3. Then we have 4 choose 2. We have 4 choose 1, 4 choose 0. In the ith row, if you consider this the 0th row, and this is the first and this is the second. So ith row is in terms of zero-based indexing. We're going to have I choose I, then I choose I minus 1, then I choose I minus 2, all the way to I choose 0. Okay, so this is something that's a little bit interesting in terms of Pascal's triangle that I just thought I'd point out because it'll help us figure out what we're doing for this problem here. So first off, I kind of want to move this to look a little bit more like a triangle. I know that the problem sort of talks about it as a 2D grid, but it really is a triangle, where every item is the XOR of the two things above it. Right, so this item is the XOR of these two, this item is the XOR of these two, and so on and so forth. Okay, now can we use the same Pascal's triangle framework to figure out what a value is going to be? So what this value here is going to be is, or okay, let's take a step back. So we have all these chooses, right? Can we tell from these particular chooses if it is going to be a k or a 0? That's all you want to do. You want to tell is it going to be a k or a 0? Well, let's think about this. The top element is 1, right? And this 1 comes from adding 1 and 0. So it is this, right? So if the element is odd, like a 3 here is odd, this means it includes this element on top an odd number of times. If the element is even, this means it includes the thing on top an even number of times. Now, what do we know about XOR? Well, if it includes the thing on top an odd number of times, then it's going to be k. If it includes the thing on top an even number of times, it's going to be 0. So all we have to do is calculate these choose values, mod it by 2, and that's going to tell us if it's k or 0. Now, for simplicity in terms of what I'm going to discuss next, I made a slight tweak here where instead of this being 3 choose 3, 3 choose 2, 3 choose 1, 3 choose 0, I just swapped it. So 3 choose 0, 1, 2, 3. And because it's symmetrical, this works. So the ith row is just I choose 0, 1, 2, all the way to I instead of backwards. It's the exact same thing. If it was backwards, both are valid, but this just makes it a little easier to think about for the next part. Okay, so now all we have to do is compute all of these values for the ith row. Now what happens if we actually try to compute these values? Well, these values can go like basically up to I to the power I, approximately. So it's, or I want to say, this is a little less than this, but it's definitely very big values. And they're definitely going to overflow. So you could try to compute, I to the power, or I choose n, but if you, and then mod it with 2, but it might overflow. Actually, most certainly will overflow. So one thing that we can do to solve this is notice that we only need these values mod 2. Okay, so in this problem, I'm not going to go into like mod inverse and division once you mod values. But if you were familiar with mod inverse and division once you mod values, you can just implement it through that path. The reason I'm not going to go into that for this problem is because there's actually a lot simpler solution to this problem. So yeah, I don't want to go, I think going into mod inverse for this problem is a little bit of overkill. Okay, so if you do know that and you want to, like in a contest, I'd probably just implement it out of simplicity because I'm very familiar with the code. So if you are familiar, it might be just a reasonable thing to go and do. But if you're not familiar with it, no need to worry. We'll get into how to do this without it. Cool. So we need to know these values mod 2, right? And when we think about like these, if these values mod 2, we're essentially trying to figure out, is this value even or odd? Now note that if you multiply an even number by an odd number, I should write this here. Sorry, this was a little bit earlier, but I was just saying all we need is these mod 2. Okay, if you multiply an even number by an odd number, we get an even number. Multiply an even number by even number, it's even. Obviously, odd times even is also even. The only way to get an odd number is if we multiply an odd times an odd. What does this mean? This means that the only possible way that I choose 2 is going to be odd is if the numbers we're multiplying are all odd. So our I choose 2 is going to be or I'm going to say like we're actually looking for the nth row, right? So like n equals ith row. So we're going to do like n choose 2, n choose like x or something, right? Or NCR. Let's just, because I feel like that's common notation. It's going to be n times n minus 1 all the way times n minus r plus 1 over 1 times 2 times 3 all the way up to times r. Okay, so in order for this to be odd, we need to divide out all the even parts on the top need to be divided by something on the bottom. This means the powers of like the number of factors of 2 that are in the top need to be equal to the number of factors of 2 on the bottom. So for example, if on top we have 2 times 3 times 4, and on the bottom we have like 2 times 2, right? This will cancel, but we're left with a factor of 2 on top, so it's still going to be even. If this has 2 times 2 times 2, now all the powers of 2 cancel. So we need to know how many powers of 2 there are in each of these. Okay, So how many powers of 2 are there going to be in the top, and how many powers of 2 are there going to be in the bottom? And when we do n choose r, we can just compute these values, and we can just, like, if the numbers are equal, then it's odd. If the numbers are even, then it's even. Or sorry, if the numbers are not equal, then it's even. If there's more on top, then it's even. Okay, so now all we have to do is this. Now, one thing I'm going to point out is the solution mentions something called Lucas's theorem. And essentially what the solution here says is, if n and m equals m, then m choose n is odd, otherwise it's even. So you can actually code this up a lot shorter using Lucas's theorem, and there is a bit of code here that just does something just like that. And the times to be here is what they meant as like k. So this is using Lucas's theorem. The code is very, very short. You can Google and use Lucas's theorem and discuss all that. However, for this problem right now, we are going to use this method right here of counting the powers of 2, just because in contest, if you're not familiar with Lucas's theorem, this is the more intuitive thing to come up with, and this is the method that I came up with when I was working on it, right? So yeah, that's why we're going to work on it, because for Lucas's theorem, if you know it, you get it, but if you don't know it, what do you do? And I don't want you to think that you can't get this problem without knowing it, because there's this very valid algorithmic solution here. Okay, so you want to count the powers of 2 on top and the powers of 2 on the bottom. Cool. So if for a value n, we just loop through all the values in the row and try to compute this formula, well, there could be up to n items in this formula. So this will be n squared. And that's going to be too slow. So what can we actually do about this to speed it up? Well, one thing that we can do is, notice that if we go from like n choose 1, it's going to be n over 1, and then we go to n choose 2, well, this is going to be n times n minus 1 over 1 times 2. And this part here matches. So we just add this extra term on the right. N choose 3, n times n minus 1 times n minus 2 over 1 times 2 times 3. This part here matches. Same thing for n choose 4. We're going to take this part, and then we're going to multiply n minus 3 and divide by 4. Specifically, to go from n choose I minus 1 to n choose I, let's say this equals x, we can just take the previous value, we multiply the top by n minus I minus 1, and we divide the bottom by I. So that's how we go from n choose I minus 1 to n choose I, right? And we can see that here, where we went from, oops, that's not what I meant to hit. There we go. Where we went from n choose 3 to n choose 4, we multiplied the top by n minus 3, which is n minus I minus 1, right? And then we divided by the bottom by 4. Now, recall that when we're doing this, we don't actually want to keep track of the number. You know, this value here in, this value here in the middle can get insanely high. It can get up to like n to the power n, O of n to the power n. So what we actually want to do is just know if this value is odd or even. So we'll keep track of the powers of 2 in the numerator and the powers of 2 in the denominator. So when we go from n choose I minus 1 to n choose I, what we're going to do is we're going to keep track of 2 different variables, like p2 in the numerator and p2 in the denominator. Now, if these 2 values, are equal, then this means that all the 2's are dividing each other's out and the number's odd. So for example, if p2 numerator is 2, This means that the numerator is a multiple of 4 or something. P2 in denominator is the same as the numerator. It's going to be odd because all the 2's will cancel. P2 in denominator should never be higher than P2 numerator. Why is this the case? Well, if you're familiar with this choose function, n choose I is always going to be a whole number. And if the powers of 2 in the denominator is higher, that implies that the denominator is not a factor of the numerator. So it implies that n choose I is not a whole number, which is impossible. Okay, so this cannot be small or cannot be bigger. So if they're equal, it's odd. And if this is smaller and this is higher, then it's even. So when we go from n choose I minus 1 to n choose I, for P2 numerator, we're just going to add how many powers of 2 are in this value to the numerator. And for P2 denominator, we're going to add how many powers of 2 are in this to the denominator. And that's it. That is pretty much all we're doing here. So let's take a look at let's write the code up. Well, this is problem G. Let's go to problem F. All right, so for every test case we have, let's see, max n is not 2000. It's going to be 10 to the power of 6. Let's just put 1e6. Okay, we have our value t, and then we also have n and k. All right. I actually want to go over the runtime for the algorithm we talked about real quickly, because I feel like we've not been going over too many runtimes. Let's pull up the Zoom again. Yep. Okay. So what's the runtime of our algorithm? Well, we have this row of length n that we're looping through. And for each value, to go from the value to the next value, recall that we just add this term to it. Okay, so that's O of n. The one thing is, every time we go from one value to the next value, we count the numbers of powers of 2 in the numerator and the denominator. How do you count the number of powers of 2 in the numerator or denominator? Well, you could pre-compute this for every value of n. So you could, outside of all the t test cases, for every single value, compute the powers of 2 in it. That is one option you could do. If you do that, then you're going to have your pre-compute time, which can be used for all your test cases. So you can do this in a similar runtime that it takes to count all the prime numbers, essentially. So you can do a similar, if you're familiar with the sieve algorithm, that counts all the prime numbers, you can do something similar. But we're just going to say, because it's hard to prove the runtime of that, I'm just going to give you a simple sort of method to do this here, which is for every value, when you're given a value x, we're just going to keep dividing x by 2 while it's divisible by 2. And when it stops being divisible by 2, we'll just stop. Okay, so for every value of x, how many times can be divided by 2? Well, that's going to be log base 2 of x. So we have n values times log base 2 of n. So pre-compute time will be n log n. And then when we're doing our test cases, it's just going to be O of n. So the runtime will be the sum of these, which is going to be n log n. Now, it's actually going to be faster than n log n, because when we're thinking about dividing numbers by 2, so first of all, most numbers, half the numbers are going to be odd, and then out of the remaining half that are even, half of them are not going to be divisible by 4. And out of the remaining half that are, half are not going to be, right? So the number of values you have exponentially decreases, but we don't have to worry about that right now. I think n log n is a reasonable enough estimation for a problem of difficulty 1700. So don't worry about that for now. All you need to know, this is about n log n. Okay. Now, let's say we don't pre-compute, and we just do it in the sense of when we go from n choose I minus 1 to n choose I, we, on the spot, compute the number of powers of 2 of each of these. That's going to take log n time, so it'll take O of n to go through all the items, and then log n time for this. So it'll be n log n again. So for simplicity's sake, I'm just going to do it this way because it's n log n. Okay. Okay, so we have our values of n and k. So now we need to find the, there we go. So now we need to find the nth row, right? So this is going to be n choose 0, then n choose 1, then n choose 2, and so on and so forth. Okay, so in this nth row right here, notice we go from I equals, like, from 0 all the way to the end. Now, we want to have n items in the row. So this means that the max value of I is actually going to be n minus 1. Right, because let's say that we had, why not? Let's do this third one right here. Actually, let's do the second one. So for the second one here, we're going to be, so this first column here is going to be technically like 0 choose 0. And then this second column is going to be 1 choose 0 and 1 choose 1. And this is going to be where n equals 2. So we have to subtract 1 from n so that we got this numerator here. So now once we subtracted 1 from n, we have this numerator on top. Okay, and then we're going to calculate P2 in the numerator. Oops. And P2 in the denominator. Okay, so now we're going to start off with the leftmost value. When it's going to be I choose 0, that's just going to equal 1. So P2 in the numerator is going to be 0. There's no powers of 2, and the denominator is also 0. There's no powers of 2 to start out with, so we don't have to worry about that. Okay. So then we can say, so we'll do, it's kind of weird because I wrote I here and we're going to loop through I, but we're going to make I essentially the bottom value here. Oops. Actually, let's start it at 0, just so that we print out all the different values. Okay. So now we need to know what we're printing out. Let's just worry about what we're printing out right now. So first we're gonna split this into step 1, update P2 num and P2 denominator, and step 2, print output value. Okay, so this is typically what you're gonna have in sort and sweep type algorithm. This is more like just straightforward sweep, where step 1 is you update some sort of data, and step 2 is you use data to update your answer. Now in this case, we're just literally printing it out. We don't even use the data to update our answer, we just print it out directly to our answer. Actually, we're kind of updating our answer, but it's, yeah. So step 2 is we're gonna update our answer. So let's just do step 2 first, because it's a little bit easier. If P2 numerator equals P2 denominator, what I'm going to do is I'm going to create a vector of my answer. And I just like to push my output into the answer to make it easier to print at the end, but however you want to do it is up to you. You could just print right here. You can print the output value right here. I'm going to add it to my vector array. So I'm going to say add output value to ants. Okay. So if they're the same, then this is going to mean that it is odd, right? And if it is odd, so for example, here, oh, that's not showing. For example, in n equals 2, they're odd, and then we print the value k. So if they're equal, then ans dot pushback k. Else ans dot pushback 0. Okay, now let's go to this step. We need to update P2 numerator and denominator. So if I equals 0, we said that we've already updated it. We don't have to deal with going from n choose -1 to n choose 0, right? Like, we don't have to deal with this transition from here to here if I equals 0. So we're going to say, we're only going to do this if I is greater than or equal to 1. Okay, so the number of powers of 2 in the numerator is going to increase by however many powers of 2 are in this value that we're adding to our numerator. That's right here. So we can just say P2 numerator plus equals powers of 2 in the value of n minus I minus 1. And we'll have to write this P2 function. P2 denominator plus equals the powers of 2 in the value I. Why did I put this in a function? Because it makes it really simple to just write here. I don't have to think about it, and because I'm doing the same thing twice, so I might as well. Okay, so let's write our power 2 function. It takes in a value x. So it's going to say int out, which is the answer, is 0, while x mod 2, while x is divisible by 2, we're going to add 1 to our answer, and we're going to say x is equals to x divided by 2. Now note that if you pass in x equals 0, that's bad. You should pass in x of at least 1 for this to work. If x is 0, you'll just reach an infinite loop. So don't have x equals 0. X should be at least 1 when you pass this in. But the way our function works is, I think, actually, I believe this should be the case. Let's just verify that we're never passing in 0. So when I is n, then this is going to be n minus, yeah, this will be 1. Perfect. So this should never pass in 0. Okay, now at the end, we need to print our answer. So for int I equals 0, n, or I less than equal to n in this case, because we subtracted 1 from n. Oops, I plus plus. Right answer of I. Okay, I'm just color coding weirdly for a second to make sure that's okay. And if it's not the last element, then we're gonna print in a space, and then at the end we're gonna print a new line. Okay, so let's run this on our sample. All right, let's see. Oh, one thing is we have to clear ants whenever we start this loop. And the reason I figured this out was I can see, it's just adding new things to it every time. So let's making sure we're clearing ants. Okay, now we can see that it's always pushing back k. So this is going to be an issue. So to debug this, let's test one value that's failing. So like this 316 right here is failing. So what I'm going to do is just run it on that one test case. Okay. So let's figure out what's going on. And in order to do this, what we're going to do is we're going to look at P2 numerator and P2 denominator pretty closely, because those are going to be the key values. So first what I'm going to do is I'm going to write what P2 numerator and P2 denominator should be for every value of I. So let's think about this, right? In this row, we're going to have 2 choose 0, because recall, we subtracted 1 from 3 to get 2, because there's 3 values in the row. 2 choose 1, and 2 choose 2. Okay. So here, we're going to have the P2 numerator and P2 denominator set. Okay, so when I is 0, this is like I equals 0, I equals 1, I equals 2, right? I is this value that's being chosen, and n is this top one. Okay, so here there should both be 0. Now, what about here? Now P2 numerator should be 1 and denominator should be 0. Now numerator should be 1 and denominator should be 1. So let's see. That's the issue. P2 is not returning. Out. Okay. Oh, that works. Okay. So sorry. I realized you couldn't see this while I was drawing it here. I was just drawing out what P2 numerator and P2 denominator should be as I increases. Now, if I hadn't fixed this right now, what my next step to debugging would be to print P2 numerator, P2 denominator, and then making sure that the input value is correct. So we're adding the correct value to numerator and denominator, and that the number of powers of 2 outputting is also correct. But it seems like this just fixed it. Alright, yes, so this worked on this test case. Cool, so let us submit this. And I'm going to pull this off to the side because I don't want to show my files to the world. Again, I'm sure you're wonderful people, but it just takes one person. So, alright. Wonderful. Alright, we got problem F. Alright, well, we got problems A through F. We're going to skip G for this contest. So I hope you've enjoyed this video, and I hope you have a better understanding of problems A through F. If you have any questions, or you have any comments, or anything you'd like to say about this, please feel free to leave a comment. I read all the comments, and have a wonderful day. See ya. Bye.